Welcome back, guys. So yesterday we managed to finish the block read and block writes and also make it dynamic. And we tested it. We were able to read and write without any issues, even with multiple calls. But we didn't test it on parallel because the actual use case would be that multiple threads or multiple processes can read and write, which hasn't been tested. But to do that, we also need to add a synchronization mechanism somehow, some mutex or something, to make sure certain operations are atomic and nobody else is doing the same thing at the same time. But we don't have any sort of mutex or semaphores in our case because our kernel does not have it. Today I'm planning to add one of it and then maybe also test it through to user space programs. So we can just write just add a syscall that can directly do block read and block writes, and the syscall should be called from multiple user space process and it should just work fine. This is what I have to try. Yeah, let's see. But other than that, nothing much. So a quick recap is that we are trying to write our own kernel, and so far we managed to finish the MMU layer and a little bit of scheduling, and we also have the virtual and physical separation. And currently we do have the block layer that is abstracting away whatever that needs to be done by the drivers. So the virtual file system layer can just simply call block read and block write. So, and let's see what we have wrote down yesterday. After the request done, set the index to free. We also tested this because currently as soon as the request is done, we also set the index to be free, which is specific to our implementation. This is done, but still this is only tested sequentially, so it does not really make any sense. It needs to be tested from a parallel scenario. Only then we can actually see if it's working or not, but that's for some other day. Still tested, but okay, we'll just put tested but not in okay, tested but not in parallel case for future. Okay, what about let's think about writing one mutex kind of. Yeah, this is what we need to do. We need some sort of mutex or whatever is the basic synchronization stuff. Let's just first do some research about how kernel handles these kind of scenarios and what sort of data structures they use. Maybe they don't even use data structures like that. Maybe there is some no lock based design because if there's no lock, it is actually really good because imagine a scenario where we have thousands of user processes and everyone most probably want to write to something, and even standard input output is some kind of write. Maybe that won't go to the file block layer. So yeah, but in general I believe if you put a lock somewhere here, the lock will become a bottleneck. Well, let's first do the research and see how Linux handles this case and what sort of data structures they use. We'll do the research and we'll come up with some points, and then we'll think about how we can implement it in our case. But as of now, let's just say that we need a synchronization data structure. And this is a to-do for today. And then what else is there? We also have to look into the VFS implementation, because now that the block layer is over, we can start with the actual file system layer And what I remember is that we need to build up a lot of data structures because the entire file system is just a big metadata, that is the root inodes, and it's just sea of inodes, I guess. Once we are done with the inodes, but internally it's we are just keeping track of inodes that are specific to a block. So whenever a high level operation like read etc password, we just go through those inodes, that is slash, and then we go to etc, that's inode, and then we go inside that and we find the passwd, and we check if it's a file or directory. If it's a file, we can find the sector that is stored within, and then we just call block read and block write. So in general, this was the main key, which is the block read and block write operation, because this is actually doing the actual physical interaction. The entire VFS layer is going to be a metadata, so it's an abstraction to handle blocks, because in the end there is only blocks of memory, there's nothing much. But for a user's perspective, it's much easier to think about it in terms of files and inodes, so we don't care about which sector the file is sitting in. And that's one of the reason the move operation in Linux is really fast, because if you just say you need to move a 50 GB file to a different directory, it will be instant, because only thing that needs to be done is that you take the inode from here and you place it there. That's it. The underlying block is not changed at all. But when you copy things, then yeah, you need to go through the sector, read it, and paste it here. Yeah, but this is something that I learned a long time ago. At that time, I knew about inodes, but I did not really understand. I just knew that inodes is some sort of reference, but I did not clearly understand what it was doing. But now that I have an actual implementation, and when I'm trying to get things together, to put things together and see what it was, now I understand it better, and I'm able to picture it in my mind. And now when I was explaining that example, I could actually see it in the metadata sense. Like we in the VFS layer, we just take the inode and we put it inside a different inode's child. That's it, nothing much. We don't do anything else, and that is the operation. So yeah, enough of chit chats. Let's try to get some work done. And before that, right, let's see how far we have changed stuff, because I want to make sure that we don't we have a snapshot of a working thing, so that if we make any changes, we can come back. What's the current change? Not this git diff. So we have a change in, this must be the old change, I guess. We just added the new files, and then I guess we did not commit the previous week's changes. That's why these stuff were written in the previous week. I think there's okay. We'll just okay. Let's just commit whatever there is in this folder. We have a build file change. We have kmain, mmc, and then block driver, and the final thing. Okay, that's enough. Working version. Dynamic. I see block read and write. write operations. Okay, now that we have that, let's check. Last time we committed was on April 12th. Okay, and then this is the one. I guess after that I did stream once, but I didn't add the commit here. Okay. Okay, now let's start just go through our existing implementation just once more. Let's just go through one, maybe read or write. What do we do? We have some global values that store the pointers to these objects, so we take them and we set up the requests and we set up the request values, and we keep on trying until we find a free index, and then we set those values based on the memory calculation, that is the size plus the index, and then we prepare the three descriptors. Yeah, this is what yesterday I forgot, I guess. Right now the length is hard coded. Do I take? Yeah, I am taking size as length. But size should be of 512. What is it? It should be a multiple of 512. If not, it will just throw an error. So yeah, I think we just simply have to update the size here, nothing much. And status size is the same, so it does not have to change. Anything else? Do we hard code? I still don't know if we need this memory barrier after everything, but still we are doing. Maybe someday we can think about optimizing it. Let's write it down. To do optimize the memory barrier calls. Do we need that after every line of code? Looks paranoid. Okay, I think rest looks just fine. Yep, let's just, to be sure, let's just run it. I guess we have only made one change, that is we just added the size, and I think it should be fine. Yeah, it is fine. So now let's go back to our main stuff here. Yeah, let's think about something for like a mutex. Now it's time to do some research. Linux core sync data structures. How do we call this? Sync, or maybe locking data structure? Primary logging data structure is a mutex, so we do have a mutex here, okay, which implements mutex exclusion using sleep mechanism. It is defined atomic variable to track the current owner and a wait queue for the task that must sleep when the lock is contended. Oh, okay. Uh, so it's not like the user has to. It's not like the user has to implement the while. They simply has to call mutex. Probably the mutex internally has this queue that is going to wait, and we do have other possible things, which is the spin lock is just simple busy wait, and we have read copy update is mechanism along concurrent readers without locking. We don't have to implement these stuff. Let's just implement a simple mutex first of all. Mm. What about the file system layer? How does it handle multiple users trying to user process trying to read or write using a physical using a block driver? Does it have any locks, or is it designed in a lock free org? Let's see. I have these questions, let's answer them and then we'll think about it. Multiple process through hierarchical and layered locking architecture, not single global lock. Okay, each file is associated with inode and file structures protected by special locks. Serialized using flip lock. Okay, use different level of locks to prevent race conditions during path lookups and metadata modification, to prevent conflicts with concurrent unlink operations. Okay. Okay. This design assigns hardware queues to CPU cores, drastically reducing lock contention by allowing parallel IO submission for multiple. Okay. Multi-queue block layer. Let's see this article. What does it say? Charged with managing I/O to a block system block device, it was designed in an era when it could handle multiple I/O per second. In fact, it tends to fall with modern devices capable of millions of. Not entirely surprising, it has been known for years as a significant change would need to be made to enable Alexa SATA. I'm just gonna skim through it so it'll be a bit faster. I just need some important keywords so that I can then use Claude to what is the name? I fucking forgot. I just have to mine Hmm. I just have to prime, not to mine. Yeah, it's priming. I think it's priming. Submission queues are set by queue. Node bases each submits I operation to the own queue with no interaction with the other CPUs. Just eliminated. Hmm. I didn't get anything, but I got one thing that we don't use locking in the queue layer. Instead, we use queues because if we lock, then every process is kind of busy waiting for no reason. So instead of that, you just put a queue and everyone can just pause in their requests and go back, do their work. Because anyway, the block layer, the virtual IO layer is also kind of having a physical queue. That's what is meant here. So the actual queue passes on its request to a hardware queue where the actual request is processed, things like that. Okay. Now it's time to look into this file. Let's see what's in there. There was a fix just 3 days ago. How long is this file? Because this is like a core mutex, so probably there must be hundreds of thousands of cases. Yeah, it's like 1,000 lines. Well, we'll try to finish it in 100 or 200 lines. Let's also check the mutex.h file so we can get an understanding of how the mutex structure looks like. Okay, it is using Linux mutex.h. Where is that file? Include. Fucking include. There's no fucking include. It's here. Linux. And we have probably the mutex.h. Well, I could search it, but I already started scrolling. Mutex. I don't see any definition. Maybe it's internally using an existing mutex. Oh, it has mutex types.h. No. It's here. Okay, this is the mutex. It has an owner. It has a lock. It has things that I don't even understand. Okay, fuck it. Let's. Oh my fucking god. Two and three. Control V3. Control V3. Control V0. Okay, it's here. Okay, we clear it. Okay, it's not possible. Okay, whatever. I am done with my all layer, block layer. No read and write, walking, but I need some sort of mutex struct to handle syncing between user processes. Let's see how Linux does this and what sort of design choices they have taken and what are the basic operations that are possible and what is the explanations for having those operations. Overall, explain the scenario and what is solved and how it is solved. Teach me. It's using high effort. What the fuck? Use. Okay. How do I change the fucking thing to medium? Okay. I'm getting a fucking call. What the fuck? No. Use. Call, you fucking piece of shit. What the fucking fuck? I don't know if it's even updated. And then I set this. Okay. It's just gonna waste all the tokens for no reason. It's not gonna do anything interesting. My fucking screen. Okay, now let's read. There's a lot to read. Maybe I should ask it to write to MD file so it will be easier for me to read. To touch the same shared resource, block catch entry, and I know to block driver request queue. If a task A is in middle of mutating it when task B permits and writes to its visualization, okay. And then call something that sleeps, you deadlock and waste cycles. Oh, okay. So I also have to do something with my scheduler then. So when I'm in a mutex, if I have a process that tries to lock, and then the lock is already taken by someone else, my process should not sleep because it will be using the CPU cycles. Instead, it's just yield and go back and give it back to someone else because there's nothing to do here. Okay. mm, mm, what else do we need? Anything important? Because I mean this is a fully fleshed implementation of mutex. We're not going to do that. At least we need to come up with a general walking version that can solve our current situation, and then we can build on top of it later. Okay, we have a life cycle. Let's see. Mm, owners, pin lock, and task. Okay, I didn't understand anything. Let's ask a specific question. Let's go through my block layer. I have a case where I have to make sure. Where's my case? Let's see. Yeah. The used. What the fuck did I do? global block data operations are synced between user processes. What is the minimum requirements I would have to think about, and what sort of scenarios I have to handle, and how is this case even in Linux? How does Linux to this? Okay, now we have a little bit more specific question. Let's see. First of all, we need also, guys, I wanted to give a shout out to FFFF. You guys definitely should try and use this. It's just so much fast and easy than just using grep to do any sort of searching operation. I think he's some YouTuber, and it's FFFF. Vim, just try this. This is the one, and it's really fast, and it has a MPC server, so I have connected this, and I've been using it to search things in my Chromium repo, and it's really fast, and it has some explanations of why such things as it's really fast. You guys should try it if you, and it can like bring down the tokens a lot. Okay, just like I just said, when I saw this, I wanted to talk about it. Okay, whatever, let's get back to our problem. Let's see, got it. Go to exactly what races you have, what's the minimum sync looks like, and how Linux structures the same problem. It's just allocated for descriptor slots. Yeah, classic where you check and where you use problem. Time of check and time of use, because you check it somewhere, but before that someone else might use it. So yeah, we need to fix this case. I did talk about it yesterday, because as soon as I wrote that code, I knew that there is a race there. That's what I try to look in my Chromium repo. I used to review, whenever I get time, I review the Chromium source code. And this is a classic scenario to look there, like where things are checked and where things are used. And is there a possible way someone else can alter the data between that time? But in general, Chromium V8 is like a single threaded system, so you don't really have to care about it a lot. But there are scenarios like asynchronous cases and micro tasks that can fuck things up there, but not as big as our own kernel, because here there is going to be multiple processes accessing it, so it's 100% race condition scenario, so we need some sort of luck here. And same goes for the global count. So as I said, this entire thing should be locked as one single operation, and it's not really intensive, because we only do a bounded loop and it's just 12 iterations for sure, so we can lock the entire thing. And what else? Yeah, this is protected because if the free index is already locked and we use that, then we don't need it. And this is also possible because when there's multiple people doing the same operation, this increment will definitely raise. So these are the three cases that we need to solve. One is the actual allocation within this index, which is this, and the second one is which is this plus this global count. And the second case is the index here, because this is if we get scheduled off at this point and someone has already incremented the index, then it would be an issue. And looks like this is also kind of racy. Because what if someone else incremented it but the actual operation does not is not valid for us? So yeah, this needs to be improved. Or I guess this entire code needs to be improved, because in a parallel scenario we can't assume that the value just has to be in different. We also have to check if the actual increment is relative to our operation, maybe something like that. So we do need a simple mutex lock, and we can unlock it in the end. We need to think about what this means. I don't understand. Do not hold this lock across IO weights. Yeah, because this is in it should be possible, right? Because let's say I'm in user process 1 and I'm inside the critical section, and I get scheduled off inside the critical section, and some other process tries to lock the same lock, then it should not get the lock, and it should just spend its time and go back. And when the first process again gets the CPU time, we finish the critical section and we unlock it. I think that's how it should be. Well, let's get back to it. Second case is okay, this is the increment case. Looks like we have a bug. Is indexed using avail index and not free index. Why did I use free index? Because free index is the index that is currently available. So I want to put that within this. Maybe we are not supposed to use whichever index that is free. We need to make sure we only use the available index. I don't think so because our index has maximum of 12 length, I guess, because that's the maximum length I have given. So I guess we can use any index within that. Let's double check that sometime. What else? Oh, it's like task to wake up. Okay. Yeah, it's like a synchronous thing. This would be nice to implement, but I think we don't need this as of now. So how it does is that protected with the lock, a spin lock, the critical section is tiny and submission can happen from the context that cannot sleep. Mm. Slot allocation is actually using spin lock, not mutex. Okay, actually, at this in for this case, having a mutex lock would be wrong because if we sleep, what would happen if we sleep? We have to get more understanding of what this is. What else is there? Linux hold the same spin lock across allocate descriptors. I didn't understand anything here, so we'll come back to it later. Completion side, per request callbacks. Yeah, it's better to implement the IRQ style so that once there is an uh, whenever there's a IRQ, we can handle it and see if it's a IRQ from which queue, which IO, and then see which number it is and call the specific thing. No busy poll, yeah. So we need to implement two things. We need to implement a spin lock and we need to okay, as I said, if we want to implement the mutex, we also need to meddle with our scheduler because the scheduler needs to be aware when to yield that current process, because if we try to occur whatever that is, the mutex, and it's not there, we have to yield. And if we want to yield, we need to signal the scheduler to schedule ourselves off the CPU, something like that. It's gonna take extra effort. mm. So Linux uses one spin lock for one of our use case, and for the other two use cases we don't even have a locking because we don't poll, it's gonna be IRQ based. Teach me what are the stuff that are needed for our minimal spin lock. First of all, explain the scenario and explain the use case. No, explain the idea behind it and how it can solve it. Can I enter the critical section? That should be the biggest question for it. So the asker, it will be like a tight while loop. We just keep checking. No queue, no waiter, no scheduler. Okay. If we are in a context that cannot sleep, then only way is spin locks. Yeah. Our, as I said, our fine free index is like a really short operation because we know that there is a bounded 12 requests. So we simply have a finite bounded number of instructions. Yeah, load and store is two different operation. I think I have this operation, my version. Okay, we also have to do this. Yeah, we have to tell the scheduler that You are not supposed to take me out. But how can we do that? What if the time slice goes out? About preempt. What if the time slice goes out? What if fuck me. Okay, the second one will spin forever, but it should be um, at some point it will release its right. I mean, it's fine. Is it not fine? But interrupts still can happen on the CPU. Fine if no. Okay, even the timer trick does not fire while you hold this lock. Okay, so now we also have to think about what if some other IRQ handler tries to uh, take this lock. What do we do? In that case, we need to also mask all IRQs. So we need to have some helper. I guess we do have it somewhere because I remember masking and unmasking. And if you see here, yeah, we disable, that's our first operation. We disable all interrupts, and within kmain, before we jump into something, we enable all interrupts. Yes, we enable interrupts here. Okay, but I guess the change I have to do, which is the adding a mutex, has multiple. I mean, it is touches upon multiple things, and everything else needs to work exactly. Only then this part will work. Okay, but now I have an idea of how we can use the spin lock and how we are supposed to make sure our scheduler does not remove us. But I think even if we are removed, it's just wasting cycles, so it's not really a bad thing. It's only a bad thing if when we are removed from the CPU and there is a IRQ that also tries to use the same lock. These are the two scenarios that we need to worry about. Generally, just letting it get swiped off and coming back again and finishing the critical section and going back is fine. So I guess let's write it down then. Okay, we need a separate thing now. We are not under drivers. It will be under core. It's going to be mutex the batch. if not defined, new text. Oh, fuck me. Define new text. Okay, I use 3. I have to put a number. And end if. And let's write that. So let's start with the mutex. As pin lock. 2 cases. Case where we just lock, get into the critical section, finish the walk and unlock it. No interrupts, or we did not get scheduled off. Then we have a case where we just lock, get into the critical section, and we did some work, now we got scheduled off during the critical section. Then we just the other just keeps waiting until its CPU time slice is over and come back here and finish the critical section. And then we have the third case there where we just lock and we do the same thing, same as second case, but an IRQ tries to use the same lock. Will it get it? Will it wait forever? As there is no CPU scheduling off or IRQs, so we need to make sure our lock will never be used by any other IRQs. And there is a case where we specifically tell the scheduler to turn off all. We can just use to mask off all the interrupts, IRQs. This way we get done the full critical section without even a time slice IRQ. Okay, makes sense. So so we need some sort of in general structures, and then we also need to talk to our scheduler. I thought mutex will have that, but even spinlock in some way needs bit of assistance from the scheduler to cover the second case. Maybe we don't want to cover the second case. Let's just keep it as the case one where even if we get scheduled off during a critical section, it does not matter because someone else eventually has to leave off the CPU, and we know for sure that currently we don't have any IRQs that's gonna take that that's gonna try to take that lock. Yeah, I guess that is all of the theory that we need, because right now we are not gonna, let's say, at least implement mutex. Let's start with spinlock, implement the two cases, and then test it. The test case should be two user process trying to call block write operation. So two people are supposed to call block write, and we are supposed to do it properly. This is going to be our test case, and for that we need to implement the spin lock. First, let's just implement the easiest version. We don't even have to talk to the scheduler. Yep, I think that is it. In general, we found three cases where we could potentially erase, and currently we are gonna fix all those three cases with a spin lock. But it would be better to implement an IRQ for the other two cases, but that will be too much. We'll just have it as a to-do for some other day. But right now, this is the thing that we have to implement. So someone has to... And I have a question. The spin lock objects. How will this be shared between processes? Or is it like the block read struct will have this object? Object live, yeah. Yeah, kernel is shared between processes. So no matter who tries to call it, they will have this memory. But we just have to put that lock within it, within the data structure. So so in our case, we just have to put it within this global data. Yeah, we create a spin lock that is global. We don't have to do this part. We'll just start with the a global lock, and it's going to be a static variable, and it's going to and we can allocate it in heap, because whenever we allocate this, as it when do we allocate that global data? Yeah, when we allocate this, we are initting it. We can also init spin lock here. That way, we sure know that. One more thing. Well, how do we design this spin lock? Do we? Yeah, we just landed right. We have some ARM instructions that are so. So we use ARM specific atomic read and swap operation. I think that's what we have to do. Internally, it has to use these operations that can for sure do everything. Because we have one variable that is going to set either 0 or 1. 1 means it is locked, 0 means it's not locked. And whenever someone tries to do that operation, it has to be atomically updated to 1, so nobody else can, everyone else can see that it's already updated and we cannot use it. Compare and swap. Okay. If we have this operation, then it's really simple. It's like compare and swap, but let's say we don't have it. what do? We load. What is LDAXR? And then we compare it and we move I didn't understand it. I mean, I get the gesture, but I didn't understand it. Atomically loads the lock value and marks the address as exclusively accessed. Can be reordered. So okay, so next memory operations are properly executed without ordering it. Okay, check if the lock is already held. That is whatever we value we read from here. Check if it is non-zero. We move one to a register. Okay, it's temporary register, and we attempt to store value 1. Okay, so because we have exclusively read from it, and this operation will only succeed if nothing changed during these two operations. So how does STXR provide that guarantee that it will only succeed in case nothing changed? Sets the monitor. Okay. Okay, so in case so that this is how we can confirm that we tag a memory as exclusive to us, and then we try to write to it. During that write, we again check if the memory is properly tagged. If it is still tagged, then we can just write to it and there's no issue. Okay. I mean, it's the same thing, but internally probably somehow they have some mutex. So internally, how does the tag is confirmed without any race? Okay, so they do have one final place where everything is globally checked. So there needs to be someone exclusive who has access to everything. So they decide, yeah, internally it's just finally, yeah, finally without a central location, there's no way we can tell if someone else modified it or not. Maybe after quantum computing comes in, we can use entanglement to confirm if something changed or not without even having to have a global states. So go. I'm really excited about quantum entanglement. Until then, we'll just have some sort of global person who is keeping track of things. Updated atomically. Yeah, let's just write this down too. So we do have a small understanding of what we need to write. So let's write type def structs. Spin lock. And it's going to have one volatile event 8 have to include std int.h event 8 lock, and it's going to be spin lock. Okay, we have the lock, and maybe we can also add the function pointers inside it, so they can just call lock, things like that. Or we can pass around it. Anything is fine. And void. No, it's going to be bool lock spin try lock, and it's going to take a spin lock. No, it's going to take a spin lock. Let's just make it a pointer. A spin lock and it's a try lock, try unlock. Spin lock, spin unlock. Let's just implement two these. Yeah, I think that should be good. And we write the internal operation using this load xr and stxr, so we can have the atomic operation. Okay, I guess I'll just put that into to do. LDXR and STXR. Add some tests. With multiple users trying to read block. Okay guys, I will try that next week then. But in general, today we managed to understand how spin locks work and what sort of races we have in our current implementation, and also a spin lock implementation for our ARM architecture. Nothing much. We also have one use case of one example case of what we want to implement. That's it, I guess. Nothing much. Thank you guys. I'll see you next week then. Bye bye.